Hi, everybody. Thank you for tuning in. So today I'm going to share the story of a recent interesting experiment whose outcome ended up to be a library which I called the uFramework. My name is Moataz Kamel, and I work at UCT. I am with the Test Equipment Engineering Group. I support the testing of gas delivery systems, which are part of the wafer fab equipment used in the semiconductor industry. Any industry is full of challenges, and the specific challenge I have been most focused on solving is accommodating the testing needs of systems which are characterized by being highly complex, of low manufacturing volume, and customer customizable. The demanding nature of the work environment involves ambitious scheduling and unrealistic time targets. We keep working to a set of constantly evolving requirements with a lot of last-minute changes without corresponding lead time adjustments, which I believe everybody can relate to. Consequently, I developed a special interest in seeking practices that would allow coping with this environment. The uFramework was an attempt to design a development framework that exhibits the following characteristics: flexible, reusable, and I am going to define that in a minute. Adaptable, meaning that it fits into multiple coding styles, accessible to a wide range of users regardless of their level of knowledge and skills. Powerful enough for advanced users, but with low barrier to entry for junior team members. Being both reusable and adaptable entails easy integration of existing code into new projects with minimal overhead for maintaining cross-compatibility. And being open entails easy extension of existing functionalities and capabilities. Before we proceed, it's imperative that we make a clear distinction between code reuse and code pasting. If you make copies of a code from a previous project to use as a starting point in your new project, that's fine. It is better to have something to start with instead of starting from scratch. Then you may tweak it here and there to the needs of your new project. However, this does not count as code reuse. It is perfectly appropriate for project templates, but if overused beyond basic starting project templates, then probably somebody is committing serious design errors that would cause undue maintainability burden and overheads. Code reuse, on the other hand, entails the application of good, solid principles, where you call reusable and stable code and extend or override its functionalities as needed. So let's get started. And the initial case study is going to be pretty typical, a producer-consumer pattern. The consumer, meant to be a reusable hardware communication module, is a common sub-VI that we call from many of our projects, including today's demo. But for the sake of simplicity, I will just have everything flattened on a single block diagram. When clicking the connect button, the producer sends a connect command along with the IP of the device to which we want to establish communication. Our reusable consumer loop over time would need to evolve. So I will pretend that it evolved to accept an optional parameter like the connection ports in addition to the IP. How would we manage such evolution? Managing evolution is a multi-tier aspect. It involves handling different data structures, or in LabVIEW terms, this would be different cluster type defs. And it involves handling data type mismatch. For example, I have seen many PLC guys who prefer to measure digital I/O signals using numeric data types with 0 and 1 values instead of using Boolean data types with true and false values. So as the consumer evolves, it's not backward compatible anymore with our old existing reusable code. The variant to data conversion fails. And an attempt to solve that was introducing a uData object. So we replace our variant with a uData object here, And we replace the variant functions with uData methods here and there. And now the consumer could default to port 8080 if a port is not specified by the sender of the message. Note that consumer expects to parse the port as a string, but the producer may send the port as a numeric, and the conversion would happen implicitly in an error-free manner. And this enables independent evolution of the data types, thus handling the payload agnostically. Some parameters may have no relevance to the receiving loop, like the meta tag here with the value acne. Nevertheless, the existing code integrates nicely as long as the contract is honored. The contract is a familiar concept to distributed team members working independently, where they have to sit together at the early phases of the project to identify what data they will exchange. Our contract here will be what tags are of joint interest to both communicating actors. Another implicit casting here is the SSL flag. It is sent as a binary bit, but received as a Boolean, which is fine as long as the value, the exchange value, is logically represented as yes and no, or as true and false. We are definitely not going to receive John or Sally if the contract is honored. The premise here is that the expected communicated data has a known logical data type, but possibly different semantic representations. And we want to eliminate the layer which is caused by the semantic rigidity. However, if rigidity is desired for cases like working on a specific mission-critical project, or wanting to protect data integrity, or maybe wanting to optimize performance, or you may have adopted an internal manifesto within your development team that states that explicit is better than implicit, or for any other reason not to appreciate flexibility and instead perceive it as a liability, then we could seamlessly transition between implicit and explicit data casting. In explicit data casting, the data type must be an exact match, or otherwise an error will be returned. This behavior will be close to how LabVIEW's good old native variant to data function would behave. So here, implicit casting is used, but we could seamlessly transition into explicit casting by calling the strict method instead of the flex methods. And in that case, we would better use a cluster type def to convert the data. We can take it further. We may apply implicit conversion to user-defined object classes. Oh, sorry. There you go. So we may apply implicit conversion to user-defined object classes. In this one, we have a measurement object whose private data include a numeric measurement and string units. The upper loop sets the value using an accessor method. But we want to communicate that measurement to a pre-developed GUI consumer loop, which has been already pre-developed in the past to expect a numeric, as you see at the bottom. The implicit conversion can just handle that, meaning that the GUI loop and the hardware loop may have been written in different eras before the developer had started to embrace the use of the measurement objects. But the loops would still be possibly brought together to integrate existing code into brand new applications in a nice and neat manner. Or maybe you want to read the measurement as a string, and in that case, maybe the string will be implicitly represented as a concatenation of the value and the units. We can do all sorts of customizations in this area. In addition to that, tags may be handled using their nested addresses. I have a question. No, it is meant to be checked at runtime and implicitly converted at runtime. I mean, at the end of the day, the intent here is to enable flexibility and allow easy and independent evolution of data types. So we don't want to strictly define it or predetermine it at the time. So you won't get a broken wire if there is that type mismatch. However, you may use error handling for catching these unexpected situations as exceptions in runtime. So one of the things that we could do as well is handling tags using their nested addresses. So the zip code in this example may be extracted alone as address.zip code. It's up to you to decide whether you want to read the whole subcluster or are just interested in a subset of the received parameters. This also shows that the ordering of the elements in the cluster does not matter. Another interesting feature is that you could expand your data type dynamically at runtime. You are not limited anymore to predetermining at edit time what the cluster elements would be. We may append elements at runtime, similar to what we could do with JSON or XML strings. For me, this has worked as a magical solution with regard to managing my connector pains and enhancing code readability. What I say here is equally applicable to passing data from one sub-VI to another downstream sub-VI, or for cascading data from an actor to another, meaning that an actor receives data, it appends some more data and sends the results to a third actor, which appends more tags and sends that to a fourth actor, and it keeps going that way. So let's implement this diagram. Again, instead of using sub-VIs, I will just flatten the code in a sequence structure for the sake of the clarity of this demo. But in practice, you will implement each frame as a sub-VI that corresponds to one of the sub-VIs on the screen. So first, we initialize the data with the name and year of birth, and the sneak peek terminal shows the list of data elements that are moving on the wire. Next, the age is calculated and appended to the UData objects. Then, on the third frame, the income data is processed. It checks if the age is greater than 16 and appends a Boolean showing eligibility to drive. The contract here is to have a tag called age, whose value will be checked for determining eligibility. On the other hand, for the second frame, the contract would be to look for a tag called YOB, meaning year of birth. It doesn't matter whether we are calculating the age of a person or a machine. It doesn't matter whether the context of the top-level application is checking people's eligibility to drive or checking if aging machines are due for scrapping. You may reuse the sub-VI whenever an age calculation is required. It has become a cohesive sub-VI with a single responsibility. You may just pass to it any collection of data coming from different top-level application contexts, as long as there is a year of birth among the incoming data. The VI will behave the same, regardless of which cluster you use to initialize. It appends the age in both cases. Take a second to look at both examples. And each module can evolve independently. At a certain point of time, maybe the can drive calculation will evolve to include an array of the states or countries in which that individual is allowed to drive. Any of the other sub-VIs that are not interested in this new array will not know that it exists. You don't need to relink the rest of the common VIs to a new or to an updated type def. This could raise a concern. Is there a potential for data collisions, like multiple actors evolving independently and all ending up using a Boolean called eligible, meaning that the value for eligible to obtain a tourist's visa may accidentally override the value for eligible to be employed? This is possible, but it could be managed through error handling. There are always compromises when it comes to design decisions, and the value of choice is the highest value that this framework is meant to bring. any flexible aspect could be shut down if it will turn into a liability, or otherwise it may be leveraged along with some measures to protect data integrity. So here I do it. I calculate the age, then later on, I introduce an action that jeopardizes the integrity of the data and tries to write 199 to the age data member. Below, we could see that this has been modified, and we get a true at the replace terminal. We could use that value to revert the changes by reading again from the upstream wire and throw out an error, or to simply accept that, because in many cases, replacements are just allowed, like updating the temperature reading every few milliseconds. That value would be meant to be overwritten safely on a periodic basis. Here is another example when replacing cluster elements. Again, the error handling strategy might, if relevant, include a check that the replace tags are false or that this array is blank. If there are replacements, the list of the replace tags may be retrieved. Then our error handling strategy may determine whether this is allowed or unexpected, and thus injecting errors when replacements are not anticipated. And this will suggest that accidental collisions has occurred due to the independent evolution of other software modules. Now that's enough talking about UData. Moving forward, you should be able to envision how payload data will be exchanged between actors or parallelly executing loops. Whenever you want to send a command message and attach some message data, the message data or the payload is going to be a UData object. The receiver will read the data and look for the tags of interest. So are there any questions before we proceed? All right, I think we are good. So let's start again with the simple LabVIEW's native producer consumer template. The thick line on the front panel is the border between the two loops. The producer sends a connect command, and the consumer processes it by simply showing the received command on a string indicator. One of the primary goals of the framework is to streamline things with what different people from different backgrounds may be used to. That way, the framework has a low barrier to entry, and onboarding newcomers should be easier. So here I do it. I replace the queue functions, clean up. We are not sending any payloads for the time being, and replace the unbundle node with a property node. And now that's a new VI with the same functionality as the previous one, but it is in a better shape for fitting into the framework, though still looking familiar and intuitive for an entry-level developer. If we have a payload, that's going to be a UData object. So when trying to bridge the gap when explaining it, I would say that this is simply this, and this is this, and the bundling is replaced by that set tag method. Let's add a reply. I will remove error handling here for the sake of simplicity. Then if time permits, we'll get back to the error handling specifics. There are some exciting stuff that this framework does with regard to error handling. So here we go. So we create a custom user event for messaging the producer loop. And an indicator to show the received reply command. And an important aspect here is that the sender passes in its own reference to that simple send sub-VI. Then The consumer processes the command and sends back a reply. This is comparable to the send self-addressed message from the NI's actor framework. But here, it's very straightforward for the consumer loop or actor to attach a payload to the self-addressed message if needed when sending back a reply. And this should fit nicely regardless of the design pattern the team members goes for. So now I create a case for processing the connect message. And here I will just send a blank reply. But typically there will be some code to connect to the hardware and then send a reply at the end of, after the connection has been established. That reply might be the serial number of the RS-485 benchtop instruments that we have just connected to, as populated digitally by sending an IDN command. Let's go here. Here we are. So we may also have a feedback from the consumer loop, depending on whether a successful connection was established. Naturally, there will be some code that executes in the consumer loop, then an error cluster is returned. If connecting to the hardware returns an error, and the hardware communication loop is not supposed to keep retrying to connect, then the architectural requirements will determine if the producer loop should know about it. There are valid use cases where the error should remain encapsulated in the bottom loop, and there are valid use cases when the top loop should know that an error occurred when the message was being processed in the consumer, especially if there is no explicit reply coming back. If the developer chooses to communicate the error-free status from the consumer to the producer, all what they need to do is to wire the error out from the hardware connection code to the error id terminal of the send reply method. So let's see it in action. When the producer receives reply, it checks for the acknowledgement status. And when the consumer executes the code and pass the error wire to the send reply, a reply is always sent regardless of the error status. However, that reply contains information about the resultant error. So we can see it when it is error-free, and we can see it when an error has occurred when processing the connect command. The consumer loop needn't be coupled to the producer loop in the sense of knowing what reply command the sender or the producer expects. By default, it is the same as the original message with a re prefix to indicate that this is reply, but the producer may decide to receive a customized reply command instead. So now the producer specifies what reply it expects, allowing the use of the hardware acquisition consumer loop in multiple applications. In this example, we wrap the loop into a reusable VI and assemble an application with two devices. The producer can tell the difference between the incoming replies. So first we add some delay time to simulate connection. Then wrap the consumer in a sub-VI and make it re-entrant. Call two instances of it. Have the producer identify when each one has connected. And here we go. Now we may act upon that. The producer may, for example, have to wait until all of the hardware modules in the application have all come online before proceeding forward to initialize the test sequence. So far, I have been using asynchronous replies. The sender of the original message keeps doing its own stuff until a reply is received. In the previous examples, the producer receives an asynchronous reply as it keeps processing user interactions that occurs on the GUI while waiting for a reply. In some use cases, synchronous replies are desirable. Synchronous replies block execution and stalls data flow until a reply is received. So let's try to do synchronous communication, all while leaving the hardware loop intact, thus maximizing its reusability. In this example, the same sub-VI from the previous example is reused as is. The top level VI sends a connect command, then it blocks data flow until a reply is received. Then the top level VI does some stuff. The two-way blocking message VI could equally be used inside a loop as well, but this should always be done cautiously and after identifying a good reason for the specific use case. Typically, such use will not be desirable due to the risks of deadlocks if not managed properly. The takeaway so far is that the application here runs a different context, but the hardware VI that we created keeps fitting into multiple top-level configurations. We have seen it in the following situations. We have seen it replying to an event-driven producer loop. We could possibly have it reply to a queue-driven producer loop, or to a launched uActor, as we will see later, or to any other transport, as long as you leverage the openness of the framework. We have also seen it replying with a custom reply command as required by a new producer in a new application whose expected reply commands may be different from what the producer loop in the original initial project expected. And we have only seen it replying with execution blocking synchronous messages or non-blocking asynchronous messages. All of these situations required zero changes to what presumably is a reusable hardware sub-VI. Let's get back to inter-process communication. Here, we have the consumer attaching a reply string as a payload. But generally speaking, it is not optimal to allow one-to-one communication in between multiple parallel processes in our application. Alternative strategies include cascading messages across the actor calling chain, where each actor may only communicate with either its callers or callees, meaning the nested actors it has launched, or a central message dispatcher may be used, or a broker may be leveraged. I am going to focus on pub-sub configurations. In a pub-sub pattern, actors or subscribers subscribe to events of interest or to event topics of interest on a common bus. Each actor expresses the topics it wants to listen to, which allows total decoupling between publishers and subscribers. It also facilitates managing the communication references. In this example, we will use the same hardware loop that we created previously, but this time, instead of passing in the reference of the consumer's queue into the producer loop so that the producer could use it for messaging the consumer and sending the connect commands, we will instead use a pub-sub configuration when assembling our top-level application. The idea here is to allow smooth transition between communication patterns, moving seamlessly from one-to-one communication into pub-sub communication, leaving room for making a variety of design decisions depending on the high-level application requirements, while maintaining modularity and a good level of existing modules reusability. So first, we launch a broker. We register the consumer loop as a subscriber. And in this example, we use the default subscription policy, which is subscribing to all topics. Then we register the publisher loop as the producer loop as a publisher. And instead of passing the reference of the consumer's queue into the producer loop, we now pass in its own publisher registration. And now this functions exactly like the one in the previous example, meaning that we ended up with two reusable modules. The upper loop is a reusable module that would seamlessly integrate in a multitude of applications regardless of the chosen architecture by the system engineer. And similarly, the bottom loop integrates seamlessly in different applications regardless of the communication strategy decided by the software architects. Note that we fully reused both loops. We did not recycle them. We did not copy paste. We used them as is without touching their internal code. We just passed in a different transport before stepping into the loop. This, in conjunction with implicit data typecasting and the data-agnostic payloads, can allow high levels of flexibility and reusability. Reiterating that we get that with a low barrier to entry. Onboarding new developers is easy, since we can use their existing knowledge as a basis for bringing them into the framework. Now, let's start encapsulating these loops into reusable modules. The recommended approach for doing so in the uFramework is to create a uActor class, but you may choose to do it in any other way if desired. I like the actor framework, it's great. However, one of its major drawbacks is the proliferation of message classes that occur as the application grows. This is something that I don't like about the command design pattern. Using string commands along with dynamically defined payload data types has worked for me more solidly, and it facilitated better decoupling of software modules and libraries. So in this implementation, I create a uActor that inherits from the uObserver, create an override to the execute method, extend the behavior of the parent by implementing a connect action, basically, upon receiving a connect message, it pops up a dialog box that shows the baud rate. It defaults to 9600 if a baud rate is not specified by the message sender. Let's hold on briefly and look at the possible configurations for the method overrides. We may implement overrides by creating a dynamic dispatch method and associating this method with a command string. So in this example, the hardware children classes may override the dynamic dispatch connect method. And this method will get executed whenever the actor receives a connect command. Or we may directly override the execute method itself. By default, call the parent method. And this allows children to behave like parents unless a specific concrete override is provided for a specific command. In this example, receiving a connect message does some stuff and then immediately starts a message pump to enqueue a poll command once every second for an infinite number of times. This may be classified as either an override or as an extension, depending on whether the parent class has an implementation for processing this specific incoming message. If the parent handles the connect message, then this implementation would classify as an override, meaning that this case in the frame will execute upon receiving a connect command instead of the parent's connect code. However, if the parent does not have an implementation for the connect incoming command, then this is classified as an extended functionality, meaning that this class has extended its parent actor class, allowing it to have an implementation for the incoming connect command, which the parent wouldn't be able to handle at all. Or maybe the connect command would call the parent method and extend its functionality, thus allowing the children to either totally override a specific message processing or extend the existing parent implementation by calling or not calling the parent methods. Or we may always call the parent methods and extend that. In this case, it calls the parent method for all incoming commands, then does some extra stuff for select cases like the incoming connect message. We might have included throwing out an error in the default parent method to return an error when receiving an unknown command. If we choose such implementation, then in the screenshot, we will have to clear that specific error code before calling in the extension case. The takeaway is that it is possible to support a multitude of design decisions. Now that the code is encapsulated into an actor class, we could directly message an alive actor by passing its reference to the main producer loop and letting it enqueue a connect message. when the connect message is received, a pop-up dialog box will show the baud rate in accordance with our implementation a few slides ago. As per one of my coworkers who was not a very object-oriented person, our new implementation has the slave loop at the bottom drawn as a cube instead of a flat square sub-VI, as we used in the first example of today's presentation. With the create action being renamed to launch and the destroy being renamed as stop. But other than that, we are basically still using the very same event-driven producer loop that we created at the early start of today's presentation, which sends a connect command by wiring in a connect string to the simple send sub-VI. And the communication mechanism that we are using here is one-to-one, meaning that we pass the transports reference to the actor, to the producer loop. We get the expected behavior. But let's send some payload. The payload will include irrelevant values and a baud rate, which is something that the hardware looks for. Thus, we will get a modified pop-up message with the new baud rate. Next, let's create an assembler actor that will launch a hardware actor and a GUI actor. The communication will be mediated through a broker. So none of them will require the reference to the other actors in Queuer. If we decide to go that route, then the framework will automatically launch the broker for us and handle the registration, providing a very handy turnkey solution. For the sake of maintaining the simplicity in this example, there are some omitted details, so you may ignore them. That would be okay for the purpose of the demo. So we wrap the producer loop into an actor, which sends out a payload that includes an irrelevant tag for the owner name and a baud rate. So basically, this is the producer that we have been using, but it's now incorporated into the actor's the actor's core methods. And this is the very same actor that we have been using already from the previous slides, which looks for the baud rate and pops up a dialog box showing the baud rate. Next, we need to assemble our application. So we create an assembler actor and a launcher VI. And there we go. The takeaway here is that we have used the very same hardware actor from the previous example, but this time in a pop-sub configuration instead of direct inter-actor one-to-one communication. And we can now assemble a very clean application. The presumably reusable code for the hardware actor could be used in a multitude of top-level configurations, leaving room for the system architect to make a variety of application-specific design decisions. Existing code pieces stitched together nicely without the need for any low-quality duct tape. There are endless use cases to discuss, and it will be impossible to cover everything. But let's go through a few quick use cases in the upcoming 10 minutes. Broadcasting a connect message might be meant to force all alive hardware actors to connect to their corresponding hardware devices, or we may want to selectively broadcast messages intended for specific actors, like commanding Visa driver to connect or commanding DAC-MX driver to connect by publishing a Visa.connect or a DAC-MX.connect message to the common broker or bus. The problem is that the code that we developed in the previous example reacts to a connect command. So in order to use the code as is, we need to implement selective subscription and message translation. Since this is an application-specific requirement, it is implemented at the application's assembler level. This boils down into the following problem statements. Number one, subscribe only to messages with a Visa prefix. Number two, implement a message translation to truncate the prefix. So Visa.connect is handled as connect, because the string connect is what our reusable code expects to receive. Number 3, other actors who are not subscribed to topics that start with a visa prefix will not react to that published event. Assume we have a button on the GUI to connect to the serial devices and another button to connect to the DAG devices. This event case on the screen handles the value change events of the visa.connect button. Then it broadcasts a visa.connect command. So as the assembler, we pass in a custom subscription policy before we launch the actor. And now my hardware actors reacts to this broadcasted command. If we attempt to broadcast the DACMX connect message instead of a Visa connect message, then our existing hardware actor will not react to it as it is not subscribed to this topic. This is open, meaning that you can create application-specific subscription policies, such as subscribe to topics whose third letter is not letter T, or subscribe to topics that consist of 6 alphanumeric characters, where the first 2 are numerals and the last 4 are alphabets. And don't ask me why. Frankly speaking, I don't know why someone will want to do that. But the takeaway is that the framework is open. You may easily create custom policies to address your unique requirements by creating new classes that inherit from the policy class. This also applies to publishing policies. So in this example, I revert back to broadcasting a connect message. Then I will subscribe to topics based on the third letter in the string command. So I create a policy to inherit from the uPolicy class, add a string to the private data, create an accessor method, implement the criteria as an override method. So the topic is deemed relevant when the third letter of the string matches the letter that has been passed in when subscribing. Now we go again to our assembler and replace the default subscription policy with a custom policy that we have just created. And now we subscribe to topics whose third letter is X. Now nothing happened, and the reason nothing happens is that the third letter of the broadcasted message is S, it's Visa Connect. So this actor is only going to reply to, or it is going to react to events whose third letter is X. Now let's subscribe to S instead of X. Oh, is that N? Yeah, I was broadcasting connect, sorry. So here I am broadcasting connect. So we are looking at the third letter of connect. And now that one will react to the connect event because it fits the policy. To summarize, when assembling the application, we define how the launched actors will interact with one another. Similarly, we can create custom publishing policies. An example use case is having a hardware actor that communicates with a benchtop power meter and publishes the latest measurements to a topic called Volt. We can launch multiple instances of this actor for concurrent communication with multiple power meters, and we differentiate between the published measurements by adding a prefix. So the published topic becomes line1.volt or line2.volt. So this actor polls for a measurement at a rate of 1 hertz. It generates a random number between 110 and 120 volts, then publishes this to a broker as an event labeled volt. It keeps polling every second because of an active message pump that was added to the connect case. So this application this is an application with a single GUI actor and a single hardware actor. Now I modify the assembler to launch 2 hardware actors and provide a publishing policy to append a prefix when publishing new measurements. A reminder, the same subscription rules apply even if you are using the flat producer-consumer pattern that we looked at earlier. Just wiring your policies. So regardless of which design pattern you go for, the framework accommodates you. For the purpose of error handling, there are a few strategies. Error may be handled internally in total isolation from the external world, or external actors may need to know something about the occurrence of an error. Depending on the application requirements, an error may stop the actor or trigger an internal actor message like reconnect or elsewise. To separate the application requirements from the core requirements, the error handling behavior may be overridden at the assembler level. There are two error handling overriding modes, conditional and superseding, and this is meant to address the differentiation between core requirements and application-specific requirements. But let's set the details aside for now. Let's assume in our example that we have an uncommon situation where an application requirement dictates that an error is handled simply by calling the NI lab use simple error handler. Then in another application, the application requirements dictate popping up a simple dialog box and logging to file. Even though we will be using the same code in both applications to maximize our code reuse. In such situation, you may pass an error handling object prior to launching the actor, and thus the actor will morph its error handling behavior to meet the application-specific requirements without having to modify the actor code. In otherwise, you tell the actor when you launch it what its error handling behavior should look like in this specific project or application. Error classes may be extended on demand as needed. So this is the same application without errors. And now I'm going to add a timeout error. So I'm going to inject error code 123, and it fails silently. To fulfill the requirement of the first project, I'm going to create an error handling class that pops up NI's simple error handler. Then go to the application assembler and pass that error behavior to the hardware actor. And now we got the desired behavior, and the simple error handler will pop up. Next, create another error handling class whose behavior involves popping up a dialog box to contact technical support and log to a file. In the application assembler, we pass the new error handler to the hardware actor before launching it. And now the hardware connection timeout error behavior changed without modifying the code of the hardware actor. To conclude my presentation, I'm going to revisit the abstract from my first slide. We have seen how the framework is open and extensible, allowing you to extend its functionality by the use of children classes of your own, such as custom subscription policies. We have gone through payload-agnostic messaging, which allow independent evolution of data structures used in different software modules and enables implicit data type handling if desired. The framework is designed to feel natural and intuitive for people with different levels of experience in LabVIEW. Abstracting communication enables fitting together different pieces of code easily, enhancing reusability and facilitating maintainability. Actors or loops may communicate together even if they use different types of communication transports. And the top-level application may use direct inter-actor messaging or brokered messaging without this causing any impact on what presumably is reusable core code. We have seen easy implementation to switch between synchronous and asynchronous messaging and creating message pumps on the fly, and very intuitive two-way communication. Due to time limitation, I didn't go through any performance benchmark results or any framework stress testing. Probably this is going to be the subject of a future presentation. So are you interested in contributing to this project? Please reach out to me in that case. Also, if you think that you can put this framework into some serious usability tests in your applications, I believe the framework may mature quicker when subject to extensive testing in a diverse application base. Thus, I have open sourced it to enable wider adoption. So let's check if you have any questions. Okay, so Dr. James says you can make simple error handler silent. Yes, I agree with that. I mean, don't look at the specific example. The idea is to morph them, the error behavior. So maybe you want to send an SMS upon an occurrence of an error. So apart from the specific example that I implemented, it's meant just to allow you to morph the behavior as needed. So Greg says, can I get a code for this? Yes, you can clone the repository in the link on the screen. Yes, I looked at the Messenger library as well. And to be honest, this framework is inspired by the Messenger library and is also inspired by the art actors that Dimitri Segatalian has mentioned, and it's inspired by the NI actor framework. And I had to look at a lot of architect, at a lot of frameworks out there when designing this. I think the only reason the Messenger library wasn't the one that I adopted is that it wasn't I mean, I thought it had a higher barrier of entry, and I felt more work is required to incorporate it into a lot of existing legacy code base that was defined in different errors with different designers taking different design decisions after people has left the company. So it is great, and it is a source of inspiration to that framework, but that framework was meant to take it for an extra step. The other thing was that my attempts to do very high throughput streaming application that felt throttled with the Messenger library. Maybe it could have been optimized and I didn't have sufficient knowledge, or maybe not, but that was another reason why I decided to just take the spirit of the Messenger library, but rebuild it in like a different contemporary style. All right, so are there any questions that I might have missed? So one of the issues as well I had with Messenger library was that I couldn't figure out how to implement very special application-specific translations, you know, it uses a lot of polymorphic VIs, and since I ship a lot of my code as packed project libraries, the evolution of polymorphic VIs would break the precompiled libraries. So to give credit where credit is due, yeah, I do acknowledge that a lot of these ideas were inspired by a lot of frameworks out there, one of which is the Messenger library. It was a great attempt, I believe that, well, you started earlier anyway, so this is just like a recent iteration trying to digest back everything that a lot of people have tried previously. All right, so if there aren't any further questions, then I guess we can leave it there. Thank you too for tuning in.